In this example, we're going to go back and get some practice with some of those basic current density equations. So we're given that our current density is given by 1 over r cubed times the quantity of 2 cosine theta in the r direction plus sine of theta in the theta direction, and that's in units of amps per square meter. And so what we want to find is the current passing through some hemispherical shell of radius 20 centimeters with theta between 0 and pi halves and phi between 0 and 2 pi. So essentially this is some hemisphere that is sort of sitting in our positive z part of our 3D space. So the bottom half has been removed. And so what we're going to do here is we're going to go back to our general current equation, and remember we can kind of relate this to our flux. So in general we said that our current is equal to the surface integral of j dot ds. And so in this case, we know that we're dealing with spherical coordinates, so our ds is going to be r squared sine theta d phi d theta in our r direction. Okay, and so now it's just a matter of setting up that integral, so we can say that our I is going to be equal to, now our theta is varying from 0 to pi halves, our phi is varying from 0 to 2 pi, we have 1 over r, because that r squared from our ds multiplied by this 1 over r cubed results in just a 1 over r. We then have 2 cosine theta sine theta d phi d theta. And so basically we're only considering this first term because when we do that dot product, we only have our r component coming out. So our theta component is essentially going away. Okay, so and then what we need to do is of course evaluate this at our given radius. So our radius is 20 centimeters, but because our current density is in amps per square meter, we want to convert that to meters. So in meters, our radius is going to be 0.2. So I'll even put an m there, so we have r equals 0.2 meters. Okay, so now we can go ahead and plug in that 0.2. Of course, we're not integrating with respect to r, so that's just going to be a constant, so we can pull that out front along with our 2, so we have 2 over the r, which is 0.2. And then our integral for phi, so this integral right here, we see we have no phi dependence in the integrand. So essentially what that's going to be is just 2 pi. So we have the integral will be phi evaluated from 0 to 2 pi, which is going to result in just 2 pi. So now we're left with just the integral of theta. So we have theta going from 0 to pi halves. It's a pretty ugly pi. So 0 to pi halves of cosine theta sine theta d theta. And so we can do a little change of variables here to make this easier. So what we can do is we can say, let's let u equal to sine of theta, in which case our du is just going to be cosine theta d theta. And that turns out to be pretty convenient because of course we can see that, well, here's our u, and the product of those two terms is our du. So now our expression is just going to become I is equal to our 2 over 0.2 times our 2 pi out front. And now we have the integral of u du. But of course, because we changed that variable, we need to change our limits as well. So now this is going to be the integral as u goes from. So our lower limit of 0 here is going to correspond to a 0u. And our upper limit of pi halves plugged in here for this theta value is going to be a value of 1 for u. So evaluating that, we now have, sort of combining those two terms, we have our 4 pi over 0.2, and then that just gives us 1/2. So we get that this is 10 pi amps. And so we could then say our current is approximately 31.4 amps through that hemispherical shell. So if you want to see some more examples sort of similar to this with these basic current equations, you can look on pages 184 to 186 in the textbook. And again, as you're working through those, if you have any questions, feel free to let me know.